This is problem 5D from the PowerPoint or 1219 from your textbook. And basically we have a train that starts from rest at station A and accelerates at 0.5 meters per second squared for 60 seconds. And I just drew this figure. So that's just this first bit here. So for 60 seconds, the acceleration is 0.5 meters per second squared. And then afterwards, it travels at a constant velocity for 15 minutes. So that's this. So the acceleration is 0. It's just traveling at a constant velocity. And for the time is 15 minutes. And then after that 15 minutes, it decelerates at 1 meters per second. So this one said negative 1 meters per second squared until it's brought to rest at station B. So station B, its velocity is 0. So I just drew that out here just to make it less confusing. And then what they want us to find is the distance between station A and B. And so basically I'll just break it down for each of these sections. For the first part where it's accelerating at 0.5 meters per second squared, I want to find out what that distance is. So it's a constant acceleration, and the equation is just S equals S naught. So that'll be the S at A. Maybe we'll call these different things. So A, and we already have a B, so maybe we'll call this C and D. So the position at C equals the position at A plus the initial velocity. So velocity at A times time plus 1/2 times the constant acceleration times time squared. The initial velocity is 0. And the position at A, we're just going to call that 0. So the position at C equals 1/2 times 0.5 meters per second squared times time squared, which is 60 seconds squared. And so that position, let's see, just doing it on my calculator, is 900 meters, because we had per second squared and then second squared. So S at C is 900 meters. So now we need to go from C to D. So now we need to go figure out what this distance is. And so that's this distance right here is what we're interested in. So with that, the velocity, let's see, we know the velocity is constant and we know the acceleration is 0. So we need to know what that velocity is. So we can also find the velocity at C with that constant acceleration using another one of our equations. So velocity at C equals the velocity at A plus A sub C times time. And the initial velocity was 0. So velocity at C equals, that acceleration was 0.5 meters per second squared, and then times time, which was 60 seconds. And so we get meters per second, and we get 30 meters per second. So that velocity at C that remains constant is 30 meters per second. Now with that, we can go back to our equation. So we have the position at D equals the position at C plus the velocity at C times time plus 1/2 times the constant acceleration times time squared. And remember, the acceleration is 0 because it's a constant velocity. And so we get SD equals 900 meters plus that velocity, that constant velocity times time, which would be that 30 meters per second times the time is 15 minutes. So 15 minutes, and minutes and seconds don't work, so we need to know, so we have 60 seconds and 1 minute. So minutes cancel out, and then we get seconds, and the seconds cancel out, so then we just get meters. And so we get, I'm just going to calculate it. We get 27,900 meters. So that isn't quite the full answer. I'm just going to make this a different color. So now we have that, now we've gotten to the position at D, but we want to go all the way to position at B, at station B. And so the position at B, we don't know the time for that, but they did give us the deceleration, and we know the initial velocity and we know the final velocity. So we can figure that out. So we have the velocity at B equals velocity at D plus acceleration times time. The velocity at B is 0. So 0 equals the velocity at D was that initial velocity, which was 30 meters per second, plus, and then the acceleration was -1 meters per second squared, -1 meters per second squared, times time. We're interested in that time. So the time equals 30, and we have meters per second, and divided by the meters per second squared. So meters divided by meters cancel out, seconds, and one of those seconds cancel out, and that moves it up to the top, so we get 30 seconds. So that's the time from D to B. Now that we have that, we can go back to that equation that we've been using with constant acceleration. And so we get S at B equals S at D plus that velocity times time plus 1/2 AC times squared. And the, let's see, so SB equals, SD we found before is 27,900 meters plus the velocity at B times time. Yeah, or sorry, it's the initial velocity at D. So the velocity at D was that 30 meters per second times the time, which was 30 seconds. And then plus 1/2, and then the acceleration, which was -1 meters per second squared, times time squared. So seconds cancel out, meters per second squared over second squared cancel out, so we just get meters, and we end up getting, let's enter it in my calculator, get 28,350 meters. So that's our answer for that one. So it's 28,350 meters to go from A all the way to B.